Alright, continuing the programming of my motor control board, which I've designed in KiCad. In this video, I'm going to be continuing to implement the architecture for the SPI gpio controller of the type mcp2317. What we want to do here is to make sure that this gpio controller appears to the rest of the system just like any other gpio. The pins that go into this gpio controller will be used from several different drivers, and we don't want to have any hard dependency from some driver to the type of gpio that it's going to be using. And the way I've implemented this in my firmware is through the use of the device tree. So I have very generic drivers which are then defined through the device tree like this. So we have gpio1 is bound to SPI3, and it uses SPI3 control pins, and these pins are referenced to the STM32 GPIO. So this is GPIO G pin 15, 3, 4, and let's see, this one is actually wrong. Oh, yeah, this one is right because it's GPIO D. Yeah, so this is the reset for the second chip. So I have two of these chips on my board. Here's one, and the other one is to the side here. That's the other one there. What I want to do now is to add the definitions for these pins to the device tree. So the pins, some of the pins are going to be configured as inputs, some of them will be outputs, and some of them will have pull-up resistors, like for example the switches here, or may need to have pull-up resistors. I think in this case we probably don't need pull-up resistors because this is connected to the debouncer chip, which already implements all of the logic necessary for both debouncing and interfacing to the switches. But we still need to configure some of them as inputs, some of them as outputs. So this is going to be a GPIO controller that has 16 pins. And let's add the code that's necessary for configuring this through the device tree. So it's going to be done in a similar way as I've done here, but we'll have pin control, a pin control option here. Let's see. Yeah, and this is going to work really well because then we can because this GPIO essentially registers a generic GPIO driver. We can then reference this section from any other driver or several drivers, and reference this in the same way as we do with GPIO here for the control pins. So all we have to do here is encode the settings for all of the pins such that the driver can read them and configure the chip with the desired settings. Currently my implementation doesn't have support for dynamic reconfiguration of the pins, but I could easily add that as well. So I'm going to be using definitions that I'm going to have to define in a header file. When the device tree is compiled, the standard way of compiling the device tree involves running it through the C++ or running it through the C preprocessor, which is then able to replace things like this with proper definitions. So the preprocessor we just replace the text with whatever is defined in the included files. In this case, we need to have definitions that are specific for this chip. For the let's see. For the index of the pin, I don't think we actually even need any. Or actually, I'll include an index. So it's going to start with 0 and then go to 15. Let's see what we can configure. I'm going to open the datasheet of this chip here. So we have in-out direction. We have, I think this is polarity for the interrupt. ipol A. Is this the interrupt polarity? Oh, okay. So maybe this is defined as ipol without any letter. Yeah. Input polarity port register. This sets what exactly? Ah, okay. So you can actually invert the GPIO pins, which is nice. Could be useful sometimes. Let's see. So what else do we have here? We have GP interrupt enable. So this enables interrupts for each pin. Pull-up resistors, gpio, whether it's input or output, and output latched data. So this register is the data that is going to be sent to the output when the pin is configured as an output. So it's really not that many settings. It's just many registers because it's one register per port. We have 2 ports. So I guess we could just we could set the polarity, interrupt, and pull up, whether it's input or output, and then latch data. We don't need to. Yeah, that is, we don't care about that in the device tree. Let's see. Or actually, gpio A register is. I guess this is the input data and this is the output data, and this is the direction. Let's see, gpio A. Interrupt. Reflects the logic level. Okay, so this is a read-write register, which basically can be used to access the GPIO pins. Great. So let's see. So I prefer to start with kind of like a sketch of what I want to achieve, and in this case, I want to achieve something like I set the index of the pin. And it's good to have index here because we may not want to configure all of the pins. So we have 2317. We'll use a prefix for all of the defines for this driver so that they are globally unique. So mcp2317, we could actually combine all of the settings into a single byte, or a single integer in this case. So we have mode, we have, let's see, mode in, or let's call this dir, and let's have a look at the actual pin that we have, PA0. That would be overcurrent, so it's an input, and 2317 PUPD. We don't have pull down, so we should have pull, or let's see. We should have a pull up on this pin. So we could have like pull up, no pull, and yeah, just those two, at least for this chip. And then we have mcp2317. Interrupt. I think interrupt control is probably not relevant to the device tree here. So direction, polarity. I guess we'll just be using default polarity. we don't need that for now. Default value. What is default value? It says the compare value for pins configured for interrupt on change. Okay. If the associated pin level is the opposite from the register bit, the interrupt occurs. Well, that's good. That can be useful. But nothing that we actually need to configure during initialization. Int control, IO control, mirror, let's see. Interrupt polarity, pull up. Okay, let's start with just with just the values for pull up and direction. And I think this I think we can sort of cram all the values into one 32-bit integer, so that I can just have two fields per pin. And then we can configure all of the pins. So we have now PA1. This is connected to encoder over current 1 over current 2. So this is exactly the same principle. 2. They need pull-ups because they're open drain outputs. EEPROM write enable. And we probably actually need to have a default value. I think actually default value would be very useful here. So let's set default value here. We don't need default values; it can be 0 because it's input. But for the 3, and I'm gonna actually add comments that says what the pin does. So this will be inc1 SC, 2 SC, enable. This will be output, and default value would be let's set it to 1. PA4 does not exist. We have overcurrent protection reset, and I wonder if that is active low or active high. And overcurrent protection, right? So overcurrent, it's actually the overcurrent level. It's a digital potentiometer that's connected to these pins. So let's see here. We have 2 pins, and one will be number 4, number 5. Both will be outputs, and reset. I don't think we need. Let me see. So I'm curious actually whether it's possible to configure the pins as open drain or if they're all push-pull. let's see. So this is. Can we see the output structure somewhere? Where is the? Let's see. Can we enable for interrupt and/or in an internal pull-up resistor? It could actually be that all of the pins actually are open drain, because it wouldn't make sense to have pull-up resistors unless the pins were open drain, or at least configurable. Or maybe the pull-up resistors are just for the inputs. Interesting. This is something I'll have to check once I. Though it should say somewhere. Like, can I search for push-pull? Maybe open drain. Open drain. So there is only reference to open drain for the int pin. Does it say here? In-out pins default to inputs. Output structure? No. So are the outputs push-pull or open drain? I have no idea. Okay, I'm not going to waste any more time on trying to figure that out. I'll just start using the chip, and if something doesn't work as expected, then I can measure the outputs on the pins and go from there. So we have write enable, and the next one is not PRZ and not P. And this one will be then 5. So pin number 4 is skipped, and we have 5 and 6 here. And I guess I can just not supply any value for that, for the pull-up resistor. And then we have all of the switches, which are on. All of them are going to be inputs. So 6, 7, and then 8 would be mcp2317 do in, and no pull up there. Damn it. Two, 3, 4, 5, 6, 7, and 8. So this is what we want to achieve. Let's see if we can configure this now from inside the device driver. So in the probe method, I will add similar code to the code that I have in the gpio driver. So it's a bit involved to read out all the properties from libfdt. So I'm just going to copy this code, and I'll go to this mcp driver, and then let's see. Right, we need to bring the chip out of reset first, of course, and then we can. Let's see. And then we can just do like this. So we get the pin control node, and if the length of the node is 0, then it's an error. If it's not 0 and we have a value, then we can use the value. Read out the value. I had a let's see. I had a default property also for the other driver, but that's because I've added that feature later when I already had device trees that were using the specification without default. But in this new driver, I'm adding the field for default value, and actually. I have to add defaults also for the inputs. They're going to be all set to 0, but there still needs to be a value there so that we can just iterate through this list of integers in groups of 3. Okay, so we have value, and we can check if length. So this is just an error check to see if length. Let's check if length is a multiple of 3. If that is 0, or actually if that is not 0, then it's an error. I guess I'll actually initialize the driver anyway, but just print that message so that it's possible to see that something's wrong. Because the driver is going to be working anyway, and it's already registered. So it's better to just go like this. And then I'm going to just iterate through all of the pins. So pin count, that's the same principle. Pin count would be the number of elements. So length is actually the number of bytes. We need to therefore just do like this. So length times 4. And each item in the list is an integer, so we have 4 bytes per item. and then pin count becomes length divided by 4 divided by 3. And then we basically just follow this this structure for actual initialization of all the pins. We have the base, which is going to be a pointer to val plus 3 times c, and then we have the index. Let's see. Let's make all of them in 32s. It's just going to be simpler. So we're going to be doing some rotations and bit operations later. So we have base plus, let's see, this one is going to be actually base. Base plus 1 plus 2. It's going to be index, options, and def value. And then this needs to be sent to the chip. So this will be a set of functions that are going to be setting the registers on the chip. 2317. Let's see, set pin direction. And then this will take self, index, and then options, and we rotate this. Let's say I need to still decide how many bits I'm going to be using, but I guess we could say that it's going to be the lowest bit. So it's going to be the last bit of this options field, which is going to define whether it's input or output. And then we write the pin. So now we have to implement this to functions. And also I'll have to implement something for the device tree. So in the device tree, I'm using some, let's see here. mcp. So in the device tree, I'm using these definitions, but they still need to be defined somewhere. So I think I'm going to include them in a file that we call libfirmware. No, actually, it's going to be libdriver. Libdriver DTS mcp2317. And then in the include files, I'll create a folder called DTS in libdriver. Do we have any include folder at all? No, we don't. So let's see. So we have let's define no base package include headers, which are going to go here. And this will have DTS mcp2317H. Okay, I think that's correct. Yeah. DTS, and then we can have a header here, mcp2317H. What is the default value? Is the default value pull-ups activated or deactivated? I think it's pretty much, I think it's deactivated. Yeah. So we can set this to 0 then. Makes more sense to have pull up to in the out, and that's the only things that we need. All right. I think I'm gonna just call write reg. If index. Alright, so first of all, index will need to be ANDed with 0f to just keep the last bit. And then if index less than, no wait, is that correct? Yeah, that should be correct. And if index is less than 8, then we have the first port, and then else have the second one. And this is going to be the same code, just use different register offsets. Index. So first of all, direction. Dir A, dir B. And then I'll just rotate this by the index. So 0 to 7. And then this will be rotated by EDX. And then, because we are writing the register, we have to have local copy. And in the local copy, we'll say dir A. Oh, actually, so drag bits. It would be better to use a method that just that sets specific bits in this case. Or even write bits. So we'll specify the bits we want to write, which would be 1 dx. And then the value that's going to be written, which in this case will be determined by the option. Right, so this is much better. And then this one will use similar call, but instead we'll be writing to the B register. dir B. And here we're going to be setting all of the bits, and we're going to be setting this to the default value. Okay. And then there is also the pull up or no pull up. It's called control like IO. IPO-L. Oh, I mean, that's polarity actually. Def-val. gpio. And this will have this bit set to options. This is getting a bit messy. Actually, it makes sense to write that function so that it accepts an integer, so I don't need to do this casting here. So this would be the pin number, and then this one is setting the pull-up value. And this is just to remove the extra code here. There equals mcp2317. B. Remove the copy here, so I don't have to copy the code. I really don't like copying the code. I don't want to copy paste too much. That should work, I think. Okay. So a slight improvement would probably be to code the bit rotations as markers. See if this compiles. So I'm going to read some of the comments here. Damien writes, "Hi, nothing worked for my board. I don't know why. On Reddit, nobody checked briefly my schematic. Only looks of it. Probably have broken ESP chips from DigiKey. Without serial bootloader." I doubt that you have broken chips. I think you probably need to look in more detail what is going on with your schematic. I've looked a little bit on your schematic in one of the previous live videos. I don't know if you've seen that or if the stream broke off, but to me it seemed it was pretty close to the to the reference design. But there could be something very minor that you may have forgotten that is stopping you from actually accessing the bootloader. Because that happens to me a lot when if I, for example, have some pin that doesn't have a proper solder joint, it will prevent me from programming the chip. So I'm working with STM32, so I'm not working with ESP8266. But I could guess that it could be something similar. And what you could do to check this is to take one of your chips and just solder it onto Node MCU or something similar, some board that you know works, and then check if it works. If it works on that board, then it's something that's wrong with your schematic. If it doesn't work on that board, then possibly you got bad chips, or you ruined them, or you burned them, or whatever. But I think you should check if the chip works on a board that you know works for sure. Okay, I got plenty of errors. Error: declaration of value shadows a previous local. I love those warnings from GCC. When I have all the warnings enabled, I get very nice messages that could potentially lead to errors, but if I fix them, I can be a little bit more sure that my code has lesser chance of having bugs. So where is Val? Val is here, I think. We have Val there, and we have Val here. Okay, and I need to define obviously the registers. I'm going to define the registers as an enum. And I'm going to go to the datasheet here and see what I need to enter. So we have IDER A. Actually, no enum in this case, because I want to know what values I'm writing, like what value each variable has. So instead, I'm just going to delete this the good old way, using defines. This will be B, and next one is IPOL A. I can see slightly, like my screen is tilted, so I can't actually see the transparent, like I cannot see the data sheet through the transparent terminal because I'm looking at the screen slightly from an angle. Let's see. 1, 2, A, 3. gpint enable A. And B. Defval A. Intcom A. Okay, then there is iocon without any letter after it, which I guess is an error. Could this be, or actually no, or actually it could be an error. It probably is an error. it probably should say icon A and icon B there. So that's what I'm going to assume it does, because all the options here are exactly the same. So that tells me that this must be A and this must be B, and they're actually on the very convenient addresses here, A and B. So icon. Oh, actually no. Yeah, of course. 0A. Icon A and B. And the GP pull up. And B. Int FA. Int cap A. GPio. All at A. Alright, so I got all the registers. Compile, get new set of errors, and I'll check the chat. Well, except if you can just desolder the other chip and solder one of your chips to that board. If you solder it carefully, you shouldn't damage that board. Like I resolder chips all the time when I have some board that maybe has something broken, and or I want to test the chip. For example, when I was doing this testing on this board, I actually resoldered the STM32 to check if it was okay, and it turned out that the chip was perfectly fine, but there were other things that were not working. My VDD-A supply was not working, and that's why I wasn't able to access the chip from the JTAG interface. So it could be something similar on your board as well. Just desolder the chip. It's good practice. If you ruin it, you can buy another one. It's more of an incentive for you not to ruin it if it costs money. But at least you will know if it's a problem with your chips or if it's a problem with your board. GPio shadows declaration of previous local. Let's call them reg. Obviously, this needs to be updated. And the last thing to implement here is the write reg bits. So this function will accept the register, the bit, or several bits, and then the actual value. put it here. And the only reason I'm going to make this in 32s is because I don't want to cast anything. I can just mask out any unnecessary bits. Bits, values. And what I'm going to do here, I'm actually going to add another copy of this and call it write_reg. And we do the same transfer, but here we will have the read-write bit set to 0. And ideally, this should also mask in the address of the chip, but I have address set to 0, so I'm not going to bother for now. And then we do SPI transfer, and this should and actually return. Return nothing in this case. And I can do this like MCP, and this can be void as well. mcp2317 write_reg self_reg, and value would be mcp2317 read_reg self_reg, and mask out. We actually reset the bits, and then we set the values. Sounds like it should be right. So I should be ending this with a inversion of the bits actually, and sending it back. I could have a copy of all of the register values in my local object, but I will only do that if there is a significant delay in doing it this way. Like if it's an issue that it does 2 operations instead of 1, then I can add that optimization. For now, I don't need that optimization. Write pin, read pin. So this should at least set our pins to the default values that I've specified in the device tree. So I could check this. I could try to compile this, and I could check this with my scope once it compiles. Be a better solution here. I'm going to change this back to uint8, just to make it clear that only the 8 bits are used. And then I can cast this wherever it's used. I have to start using the shortcut for going forward and back to the next character. Like, for example, let's say I'm here and I want to go to the first underscore on this line. I can do big F underscore, big F underscore. Okay, there were many underscores there, many more than I actually saw when I first looked at it. But anyway, I could do like, for example, I can say like 3F underscore, and I go 3 underscores to the right, and then like 3 big F underscore, and I go to the first underscore. So this is very useful. I have to start using this more. And I can go forward to the semicolon using the same method, and then just delete that. Oh wait, let's see. Let's go back to the here, so like that. Damien, do you have a scope? If you don't have a scope, if you just have a logic analyzer, I suggest you get a scope, because the scope is extremely useful for doing this kind of work. So you at least know what you're actually getting on the pins. And then go back, parenthesis, repeat. And this will need to have parentheses around it. Is this going to compile? I think it did. I think it's flashing. Yep. Flash written and verified. Jolly good. Let's see. There. Okay. We crashed. Okay. Let's see. Oh, so we don't have a device tree. No such file or directory. This needs to be fixed. loop firmware loop driver. Okay, that's good. And this is not running. Did I actually build the device tree now? I need to update my build process so that if the device tree compilation fails, it should actually fail and not continue. I think the device tree got compiled. Let's see. Okay. Now it's running. So now I actually rebuilt the device tree. So I had, for some reason, it didn't build the device tree last time. Anyway, now it's running, and now I have to check if I have console, good. And I have pin control format, not multiple of 3, of course. This needs to be updated. Okay. All right, no complaints. And now I'm going to check if the pins have correct values. So I have pin, let's see, pin 3, and that would be pin 3 on PA. So pin 24. So that pin, pin 24, is supposed to be high, and pin 23 is supposed to be, let's see, pin 23 is an input. So I suppose I could check pin 24 and pin 23 and just check if the values align with what I expect. Nope, pin 24 is low. So it didn't correctly apply the settings. I'm gonna check if something is not right here. Okay, so gpio 1 uses CS pin 1. I think this is correct. So yeah, this should be gpio. GPX is the other one. Okay. I'm just gonna make sure that the other chip doesn't have value of 1. No, it doesn't. So something is not writing correctly to the registers. Oh, this FDT node, is that the correct handle? It should be the correct handle. Yeah. Console. Oh, okay. Let's see, val plus 3 times C. Oh, okay. So IO direction If it's set to 1, it means it's an input. So therefore, we need to actually replace this. Let's see. MCP. In is 1 and out is 0. And pull up, that should be correct. And then I'm going to check if this makes any difference. Will this output a 1? Nope. No 1. Okay. Do I need to put a sleep after the reset? Maybe that's the case. What is the reset? Let's see, start to ensure reset time. Okay, so internal reset. Is this microseconds or nanoseconds or what? Internal reset. Output pin. Oh, nanoseconds. Device active after reset high, 0 nanoseconds. Typical. Okay, yeah, so that shouldn't be an issue. I can dump the registers. But something is wrong here. So the value on the pin is 0 volts. It's not active. Okay. So I'm transmitting, I'm just sending the 0x40, then register, then value. Can do like this. Let's see. I decided that it's much easier to just print out the values and get an overview of everything that's happening than to have to step through the, like, put breakpoint and then step, and inspect. It's going to be faster this way. So let's see. I'm going to go here. And what is going on here? So we're writing, so we're reading 0, get FF, then we're writing FF. I think I'm doing something wrong with the bit operations. 67. 321. Okay, so read. So this line here that reads register 12, 67 is actually the value that it's reading from the port. So this should be. I'm gonna check this. So 67 means that, and 12 is port A, right? 12. Yeah, 12 is port A. So I have pin number 456 is 1, 7, and 8, and 9. 4, 5, 6. So these ones are all ones. Okay. But not this one. So this one is not being written correctly. So we're setting direction to 0. We're setting okay. Write registered bits. What I'm doing here is to invert that. I read the register. And here I write, I actually read D7, write 97. Okay. Read F7. Right. So this resets, I guess that would be which one? So that must be pin number 4. Which is here. So it will be index number 3, pin number 4. So that's when that one gets written. And then it's 67. And then it's D7. So let's see, we read 67. Oh, 67 is from another register. So we read F7, we write D7. Okay. So now that one is an output. And what am I writing to the register? Yeah, so this one is an output. And F7 and 0C. Oh, let's see. So value, am I actually writing the correct bit? I think I'm not writing the correct bit. I think I'm writing value as just 1 when I'm supposed to be actually rotating this bit. Yeah, so this would be the wrong way to do it. Yeah. So this, yeah. reference 1, and then here I'm going to do this EDX. Do like this. So mask out that bit, and I'm going to write it to of course. This is completely wrong. I was totally wrong here. So this needs to be the same code that I have for the other calls. And then this writes the correct bits, I think. So let's see, I'm actually gonna turn on the camera, I think. I should have the camera somewhere. Some window. Got the camera here. And I'm going to check this with the multimeter to see if it actually works, so that I can have it on camera. So checking pin number 4 from the end there. Let's see. Yeah, we got 3.3 volts. Actually, it's pin number. Is it pin number 4 or number 5? I think it's pin number 4. No, actually, I think it's pin number 5. I'm gonna check here because I've been checking pin number 5. Yeah, it's pin number 5. So it's 1, 2, 3, 4, 5. So that one is high. So it means we are. It means we have a driver that actually works. And the pins are getting set correctly. Next step is to have the API for toggling, or actually, the pins can already be toggled, but I just need to add some code to the interface. So I have the interface here. Let's see. Right. So here I need to add some code that just writes the value to the pin. And this is easy enough to do. mcp2317 read reg and that will be GPIO device. So self here would be, let's see, struct mcp2317 self would be container of dev struct mcp2317 dev ops. So this will give us the container value for the actual instance of the driver, and I'm going to read the register and then I'm going to write it. mcp2317 write reg self and actually the same applies here. We need to check whether the pin is less than 8, in which case it's GPIO A, or otherwise it's GPIO B. And then this I just realized something though. I'm still wrong here because I need to adjust the index. If index more than 8, then index is rotated by 4. That's 3. Yeah. So that we get correct index for the second port B. And then this one, I'll reset the pin first, or reset that bit in the red value. So it would be pin and then I'll OR this with 1, or actually value, and rotate this same number of bits. And then read pin is very similar. Even simpler. So if pin less than 8, value equals mcp2317, read reg, so if this is true, then value is 1, otherwise value is 0. And else, we do pin rotate by 3, and then this would be gpio B. Okay. And then this needs to be cast to unit 8. And that compiles. I will test this code a bit later once I start working on the driver for one of these peripherals that have some control signals connected here. I think I would probably add some functionality that reads the switches, and then I will also add the pin definitions for this one, for this interface. Alright, that's it for this video, and I hope you learned something. More videos to come on C programming of this board. You can watch the full design of this board on my channel, and you can subscribe if you want to be notified when I broadcast live next time. Alright, Damien, great that you figured out what the problem was. So, what was it missing actually? Was it missing some components on your schematic?
or I assume it actually is missing some connections outside of the board, which sounds promising. Hopefully it works once you fix the programming interface.